Here is a question that will either ruin your week or change your life, depending on how seriously you take it. What if the universe is not winding down toward darkness and silence and heat death, but winding up towards something? What if 13.8 billion years of cosmic evolution, from the first hydrogen atoms to the neurons firing in your brain right now as you listen to this, what if all of it is not random, not accidental, not meaningless, but aimed? What if the universe is building a god? That sounds like the kind of thing you would hear from someone who has spent too long alone in a cabin with nothing but mushrooms and a copy of the Bible. But here is what makes this particular question dangerous. The people asking it are not mystics. They are not gurus. They are physicists, cosmologists, information theorists, mathematicians. And the evidence they are pointing to is not feelings or faith or ancient texts. It is numbers, specific, measurable, falsifiable numbers. Numbers so strange and so precise that some of the most brilliant scientific minds of the last century have looked at them and said out loud in published papers that it looks like someone rigged the game. A Jesuit priest predicted a global web of interconnected human thought decades before the internet existed. A mathematical physicist at Tulane University used general relativity to argue that God is a provable consequence of physics. A lifelong atheist astronomer looked at the nuclear structure of carbon and concluded that a superintellect had tampered with the laws of nature. And then, in 2025, a dark energy survey cracked open the door to a possibility that mainstream physics had declared dead for 27 years. The possibility that the universe might actually be heading toward collapse, toward convergence, towards something that an obscure French priest called, almost 100 years ago, the Omega Point. But before we get anywhere near those 2025 results, before we talk about what the dark energy spectroscopic instrument found and why it sent shockwaves through cosmology, we need to go back, way back, to a man born in 1881 in a castle in central France, the fourth of 11 children, a boy who collected rocks and prayed with equal intensity, who would grow up to become one of the most censored, silenced, and ultimately prophetic thinkers of the 20th century. A man the Catholic Church tried to bury while he was still alive, and whose ideas are only now, 70 years after his death, getting the hearing they deserve. His name was Pierre Teilhard de Chardin, and the story of how a Jesuit paleontologist invented the concept of an evolving universe reaching towards supreme consciousness, got banned by his own church, died in obscurity on Easter Sunday, and then slowly, quietly, turned out to be right about more things than anyone wanted to admit. That story is where all of this begins. Teilhard was born at the Château of Sarsenat, near Clermont-Ferrand, France, on the 1st of May, 1881. His family tree was absurd. On his mother's side, he was distantly related to Voltaire. On his father's side, to Blaise Pascal. So the collision between faith and reason was literally in his blood. His father was a naturalist who nurtured his fascination with rocks and minerals. His mother deepened his Catholic devotion. By 12, he was enrolled in a Jesuit college. By 18, he had entered the Jesuit novitiate. And by his mid-20s, he was already feeling the tension that would define his entire life. He loved God, he loved rocks, and he could not understand why everyone kept insisting those two things were at war with each other. But then came 1914, and the trenches changed everything. When World War I broke out, Teilhard was drafted. He could have served as a chaplain, staying relatively safe behind the lines. Instead, he chose to be a stretcher bearer. Frontline, Champagne, Verdun, the Second Battle of the Marne. He carried wounded and dying men through mud and gas and artillery fire, and he was decorated with both the Military Medal and the Legion of Honor. But the war did something else to him, something that would take decades to fully express. Surrounded by industrialized death on a scale the world had never seen, Teilhard did not lose his faith. He deepened it. He started writing, right there in the trenches, about an idea that was forming in his mind, an idea about the direction of the universe. Not direction in the sense of which way galaxies are moving, direction in the sense of purpose, meaning, trajectory. He looked at the history of the cosmos and saw not random chance, but a pattern of increasing complexity, a pattern of rising consciousness, and he believed that pattern pointed somewhere. After the war, Teilhard earned his doctorate in geology from the Sorbonne in 1922 and soon found himself in China, where he would spend roughly 23 years doing fieldwork that cemented his reputation as a world-class paleontologist. He was part of the team that excavated the Zhoukoudian cave complex near Beijing, where in December of 1929, they uncovered a skull of Homo erectus pekinensis, better known as Peking Man. Teilhard established the geological era of inhabitation at approximately 750,000 years ago and confirmed that this ancient hominid used fire and manipulated stone tools. This was serious science, published, peer-reviewed, respected. But Teilhard was not content to simply dig up fossils and catalogue them. He wanted to understand what it all meant, what the entire sweep of evolution, from dead rock to living cell to thinking mind, was actually about. And the framework he developed was breathtaking in its ambition. He described the universe evolving through 4 ascending stages. First, the geosphere, dead matter, rocks, minerals, water, air, the realm of physics and chemistry, governed by conservation and degradation of energy. Second, the biosphere, life, the emergence of organisms that feed, reproduce, and evolve, transforming the surface of the planet into a living layer. Third, the noosphere. This is where it gets interesting. The noosphere, from the Greek nous, meaning mind, was Teilhard's term for the sphere of thought. When Homo sapiens appeared, evolution did something it had never done before. It became conscious of itself. Humans created language, culture, technology, and eventually a global web of interconnected minds that enveloped the planet like a new atmosphere. Teilhard described this in the 1930s and 40s, decades before the internet, decades before anyone had the slightest inkling of a worldwide information network. He was describing the internet before vacuum tubes were common household technology, and he called it the noosphere. But Teilhard did not stop there. He proposed a 4th stage, the culmination, the endpoint toward which all of this was heading. He called it the Omega Point. The Omega Point, in Teilhard's vision, was the final convergence of all consciousness into a supreme state of unified awareness, not a dissolution where individual minds melt into some cosmic soup. The opposite, Teilhard insisted the personality would be infinitely enriched at the omega point. Individual consciousness would not be lost but perfected. Everything that rises must converge, he wrote, and at the summit, you will find yourselves united with all those who, from every direction, have made the same ascent. He assigned 5 essential properties to the omega point. It was pre-existing, meaning it already exists as a transcendent reality, drawing evolution toward it, like a magnet pulling iron filings along invisible lines of force. It was personal, not some impersonal field, but a being. It was transcendent. Beyond the evolutionary process, it was guiding. It was autonomous, independent of the systems it was pulling forward. And it was irreversible, meaning once reached, it could never be undone. Now, here is where Teilhard showed his hand. For him, the omega point was not an abstract philosophical concept. It was Christ. He developed a theological framework he called Christogenesis, the idea that cosmic evolution is ultimately the process of Christ coming to fullness. The sequence ran like this: cosmogenesis, the birth of matter; biogenesis, the birth of life; noogenesis, the birth of mind; and finally, Christogenesis, the birth of God through the evolutionary process itself. He drew on St. Paul, who wrote that Christ holds all things in unity, and that there is only one Christ. He is everything, and he is in everything. For Teilhard, the incarnation was not just a historical event in Palestine 2,000 years ago. It was a cosmic evolutionary milestone. You can already see why the Catholic Church had a problem with this. Actually, problem is an understatement. The Church waged a decades-long war against one of its own most brilliant sons. It started in the 1920s, when Teilhard's lectures at the Catholic University of Paris on evolution and original sin alarmed the Holy Office. They suspected him of denying the doctrine of original sin, which was a serious charge. In 1925, the Jesuit Superior General gave him an ultimatum: sign a statement affirming 6 doctrinal points, or be expelled from the Society of Jesus. Teilhard signed, and then they exiled him to China, which, to be fair, is where he did his best scientific work, but it was still exile. In 1944, his superiors explicitly refused permission to publish his masterwork, Le Phénomène Humain, which he had been writing for years. Pope Pius XII allegedly called his work a cesspool of errors. In 1957, the Vatican forbade his works to be retained in libraries, sold in Catholic bookshops, or translated into other languages. And in 1962, 3 years before the reforms of Vatican II that his ideas helped inspire, the Holy Office issued a formal monitum, a public warning, declaring that his writings abound in such ambiguities and indeed even serious errors as to offend Catholic doctrine. Teilhard never saw any of his major works published in his lifetime. He died on Easter Sunday, April 10th, 1955, in New York City, of a heart attack. He had told friends just weeks earlier that he hoped to die on Easter Sunday. He was buried at the Jesuit novitiate in Hyde Park, New York, on grounds that now belong to the Culinary Institute of America. There is something darkly funny about the fact that the man who envisioned the universe evolving toward God is buried under a cooking school. After his death, friends published his works. Le Phénomène Humain appeared in French in 1955, and the English translation, The Phenomenon of Man, followed in 1959 with an introduction by Julian Huxley. The scientific reception was, shall we say, mixed. Peter Medawar, the British immunologist and Nobel laureate, published a review in the journal Mind in 1961 that remains one of the most savage reviews in the history of academic publishing. He called it nonsense, tricked out with a variety of metaphysical conceits, and wrote that it cannot be read without a feeling of suffocation, a gasping and flailing around for sense. Richard Dawkins later called it the quintessence of bad poetic science. But here's the thing about Teilhard. The people who dismissed him kept having to explain away the things he got right. He predicted a global information network. He predicted that evolution would accelerate through technology. He predicted that human consciousness would increasingly merge into collective intelligence. He predicted that the boundary between biology and technology would blur. When Marilyn Ferguson surveyed 185 leaders of the New Age movement about their greatest intellectual influence, Teilhard was named more than anyone else. His fingerprints are all over Vatican II. Flannery O'Connor titled a short story collection after his famous line, "Everything that rises must converge." The transhumanist movement and Ray Kurzweil's singularity concept are essentially his ideas in Silicon Valley clothing. And one of his most famous quotes, often repeated, rarely attributed correctly, captures the audacity of his vision better than anything else. Someday, after mastering the winds, the waves, the tides and gravity, we shall harness for God the energies of love. And then, for a second time in the history of the world, man will have discovered fire. So that is Teilhard de Chardin, a paleontologist who saw God in the fossil record, a mystic who predicted the internet, a Jesuit whose own church tried to silence him, and whose ideas are more relevant today than they have ever been. But Teilhard's omega point was a theological and philosophical concept. It was poetry dressed in scientific clothing, or scientific intuition dressed in theological language, depending on your perspective. What it was not, at least in Teilhard's version, was physics. It was not mathematics. It was not testable. That would come later. That would come from a very different kind of thinker entirely. A mathematical physicist from Alabama who decided to do something that most scientists would consider either incredibly brave or completely insane. He decided to prove God using equations. But before we get to Frank Tipler and his extraordinary attempt to demonstrate the existence of God through general relativity and quantum mechanics, we need to take a detour through something even stranger than theology. We need to talk about numbers, specific numbers, the numbers that describe the fundamental forces and constants of the universe, because these numbers are frankly terrifying. And the reason they are terrifying is that they appear to be rigged. Imagine you're a detective. You have been called to investigate a casino. Someone has reported that the house is cheating. You arrive, you sit down at the roulette table, and you watch. The ball lands on red, then red again, then red again, 20 times in a row. You could shrug and say, well, it had to land somewhere. Somebody has to be the observer in the universe where this happens. But you are a detective, and your instincts are screaming that something is wrong. Now multiply that feeling by a factor of 10 to the power of 120, because that is what the fine-tuning of the cosmological constant looks like. The cosmological constant, which controls the rate of expansion of the universe, is fine-tuned to approximately 1 part in 10 to the power of 120. That is a 1, followed by 120 zeros. Nobel laureate Steven Weinberg was among the first to articulate the problem clearly. The existence of life of any kind, he wrote, seems to require a cancellation between different contributions to the vacuum energy, accurate to about 120 decimal places. Leonard Susskind, one of the fathers of string theory, added that making the first 119 decimal places of the vacuum energy equal to 0 is most certainly no accident. Let me try to give you a sense of what that precision means. Imagine the entire observable universe, all 93 billion light-years of it, converted into a measuring line. The life-permitting range for the gravitational constant alone, on that scale, would be about 9 nanometers wide. That is the width of a single protein molecule. The window in which the universe can produce stars and planets and chemistry and life, when plotted against the entire range of possible values for gravity, is a protein molecule on a line the size of the cosmos. But gravity is just one constant. The strong nuclear force, which holds atomic nuclei together, is calibrated with similar absurd precision. If it were just 2% stronger, diprotons would become stable. All hydrogen would fuse into helium immediately after the Big Bang, and there would be no water, no long-lived stars, no chemistry. If it were 5% weaker, no elements beyond hydrogen would form at all, a change of just 0.4% in the strong force constant would render stars incapable of producing both carbon and oxygen in the abundances needed for life. 0.4%. That is not a big margin of error. Then there is nuclear efficiency, the fraction of mass converted to energy when hydrogen fuses to helium. The value is exactly 0.007. If it were 0.006, protons and neutrons would not bind together, and complex chemistry would be impossible. If it was 0.008, no hydrogen would remain after the Big Bang, and stars could never form. The universe exists in a narrow window between too sticky and not sticky enough, and that window happens to be exactly where life can emerge, and the matter-antimatter asymmetry. For every billion antimatter particles in the early universe, there were approximately 1,000,000,001 matter particles, an excess of roughly 1 part per billion. That tiny, seemingly trivial imbalance is the reason anything exists at all. If the asymmetry was 0, all matter and antimatter would have annihilated each other, leaving nothing but radiation. If it was significantly larger, the universe would have evolved very differently. 1 extra particle per billion, that is the margin between a universe full of galaxies and stars and planets and a universe of pure light and nothing. But perhaps the most staggering number in all of fine-tuning comes from Roger Penrose. In The Emperor's New Mind, published in 1989, Penrose calculated the probability of the universe's initial low entropy state occurring by chance. Low entropy, meaning the highly ordered, highly specific initial conditions that allowed structure to form instead of the universe starting as a featureless soup. The number he arrived at was 1 in 10 to the power of 10 to the power of 123. That number is so large it breaks the ability of language to describe it. Penrose himself wrote that one could not possibly even write the number down in full. It would be a 1 followed by 10 to the 123 successive zeros. Even if you wrote a 0 on each separate proton and on each separate neutron in the entire universe, and threw in all the other particles as well, you would fall far short of writing down the figure needed. So the question becomes unavoidable. Why? Why are these numbers what they are? Why is the universe fine-tuned to such absurd precision for the emergence of complexity and life? And this is where one of the best detective stories in the history of science comes in. A story about an atheist, a nuclear resonance, and a prediction that should have been impossible. Fred Hoyle was a British astronomer, cosmologist, and lifelong atheist. He was brilliant, abrasive, contrarian, and frequently right when the establishment was wrong. He coined the term Big Bang, intended as an insult, to mock the theory he spent decades opposing. He was not a man inclined toward mysticism. In 1953, Hoyle was visiting Caltech and became dissatisfied with the existing calculations of the triple alpha process, which is how 3 helium nuclei fuse together to create carbon inside stars. The problem was simple but devastating. The process, as understood at the time, was far too slow. It could not account for the observed abundance of carbon in the universe. Carbon is everywhere. Your body is made of it. The chemistry of life depends on it. But the physics said there should not be nearly as much of it as there clearly is. Hoyle did something remarkable. He worked backward from the existence of carbon-based life. We exist. We are made of carbon. Therefore, carbon must be produced efficiently in stars. Therefore, there must be an unknown excited resonance state of the carbon-12 nucleus at a very specific energy level, around 7.65 million electron volts, that dramatically accelerates the triple alpha process. This resonance state had never been observed. No experiment had detected it. The existing data seemed to rule it out. Hoyle marched into William Fowler's laboratory at Caltech, the Kellogg Radiation Laboratory, and told him the resonance must exist. Fowler was deeply skeptical, but a junior physicist named Ward Whaling convinced Fowler to let them use an old Van de Graaff generator to look for it. Within months, they found it at exactly 7.65 million electron volts, right where Hoyle said it would be. Think about what happened here. An atheist astronomer used the existence of life as a premise to predict a nuclear physics result that experimentalists had not found and did not expect. And he was right. The discovery launched the landmark paper on stellar nucleosynthesis, known as the B²FH paper, published in 1957, which explained how stars forge all the elements heavier than hydrogen and helium. It earned William Fowler the Nobel Prize in 1983. Hoyle, controversially, was not included, but the experience changed Hoyle's worldview permanently. In 1981, he published his reaction. A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. A superintellect has monkeyed with physics. That from a man who had declared that religion is but a desperate attempt to find an escape from the truly dreadful situation in which we find ourselves. Now, there are counter-arguments to fine-tuning, strong ones. The most prominent is the multiverse hypothesis, string theory's landscape predicts at least 10 to the 500th power possible vacuum states, each representing a different universe with different physical constants. Combined with eternal inflation, which continuously spawns bubble universes, this creates an ensemble so vast that some universes will inevitably have life-permitting values just by chance. We observe one of those lucky winners because we could not observe anything else. Philosopher John Leslie offered a thought experiment to illustrate the tension. Imagine you are standing before a firing squad, 50 trained marksmen, all aiming at you. They fire. Every single one misses. You survive. Now, you could reason that you should not be surprised, because if they had not missed, you would not be here to wonder about it. But Leslie argues that is absurd. The rational response is to seek an explanation. Either the marksmen were instructed to miss, which is the design hypothesis, or there are millions of executions happening simultaneously, and you happen to be in the one where everyone missed, which is the multiverse hypothesis. Douglas Adams, author of The Hitchhiker's Guide to the Galaxy, offered the counter argument. A puddle of water, he said, might look at the hole it sits in and marvel at how perfectly the hole fits it. It must have been designed for me, the puddle thinks. But of course the puddle adapted to the hole, not the other way around. Physicist David Deutsch reportedly responded that the puddle analogy does not hold water, because unlike a puddle, life cannot exist in just any universe. We are going in circles. And that, in a way, is the point. Fine-tuning is a genuine scientific puzzle, and the two leading explanations, design and multiverse, are both empirically unverifiable. As Paul Davies wrote, invoking an infinity of unseen universes to explain the unusual features of the one we do see is just as ad hoc as invoking an unseen creator. The multiverse theory may be dressed up in scientific language, but in essence, it requires the same leap of faith. So let us leave the question unresolved for now, because the story is about to get much stranger. We have the numbers. We have the fine-tuning. What we have not yet done is ask the question that connects all of this to the omega point. If the universe is fine-tuned for life, is it also fine-tuned for something beyond life? Is it fine-tuned for consciousness? And if so, does that fine-tuning point somewhere? To answer that, we need to look at what the universe has actually done with its 13.8 billion years. We need to follow the arrow of complexity. 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form. Hydrogen, helium, a trace of lithium. That was it. 3 elements. No stars, no planets, no chemistry worth mentioning. Just a vast, expanding cloud of the simplest possible atoms, drifting through darkness. Roughly 1 to 200 million years later, the first stars ignited. These population 3 stars, as astronomers call them, were monsters, composed almost entirely of hydrogen and helium. They were hundreds of times more massive than our Sun, burned at surface temperatures around 100,000 degrees, and lived only 2 to 5 million years before detonating in supernovae so violent they seeded the cosmos with heavier elements: carbon, oxygen, iron, silicon. The James Webb Space Telescope confirmed candidate population 3 stars in 2025, giving us our first direct glimpse of these primordial furnaces. Those heavier elements drifted through space, accumulated in molecular clouds, and eventually formed second and third generation stars surrounded by planets. around 4.5 billion years ago, one such planet formed in an unremarkable spiral galaxy at an unremarkable distance from an unremarkable yellow dwarf star. And on that planet, something happened that, as far as we know, happened nowhere else in the observable universe. Chemistry became biology. The earliest evidence of life on Earth dates to roughly 3.5 to 3.8 billion years ago. Single-celled organisms, prokaryotes, simple by any standard. But they were alive, they metabolized, they reproduced, they evolved. And here is something that should stop you in your tracks. Life appeared on Earth almost as soon as it possibly could have. The late heavy bombardment, a period when the inner solar system was being pummeled by asteroids, ended around 3.9 billion years ago. Life shows up in the fossil record within 100 to 400 million years of that, as if it were waiting for the bombardment to stop, as if the moment conditions permitted, life was inevitable. For the next 2 billion years or so, life remained single-celled. This is sometimes called the boring billion, and it is genuinely strange. 2 billion years of single-celled organisms doing essentially the same thing. Then, around 1.5 to 2 billion years ago, eukaryotic cells appeared. Cells with nuclei, with internal structure, with the capacity for dramatically greater complexity. This was not a gradual change, it was a revolution. One prokaryotic cell engulfed another, and instead of digesting it, they formed a partnership. The engulfed cell became the mitochondrion, the powerhouse of every complex cell on Earth. Lynn Margulis, who proposed this theory of endosymbiosis in 1967, was ridiculed for decades before the evidence proved her right. Multicellular life followed. Then, around 541 million years ago, the Cambrian explosion produced the vast majority of major animal body plans in a geological eye blink, roughly 20 million years. Evolution had been moving slowly for 3 billion years. Then it sprinted. Why? Nobody knows for certain. Theories include rising oxygen levels, the breakup of the supercontinent Rodinia, an arms race between predators and prey, or some combination of all three. But the pattern is clear. Long periods of apparent stasis punctuated by explosive bursts of innovation, and each burst produced dramatically more complex organisms than the last. And then, roughly 200,000 years ago, in the most recent 0.001% of cosmic history, humans appeared. A species that does not merely respond to its environment, but reflects on it. A species that asks why. Eric Chasson, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, spent decades quantifying this trajectory. He proposed a measure called energy rate density, measured in ergs per second per gram, as a universal metric for complexity. And the pattern he found is staggering. A typical galaxy processes roughly half an erg per second per gram. The Sun processes about 2. Earth processes about 75. Plants process around 900. Animals process around 20,000. And the human brain processes approximately 150,000 ergs per second per gram. The human brain consumes 5 orders of magnitude more energy per unit mass than the Sun. In Chasson's words, it is the most exquisite clump of matter in the known universe. From galaxies to modern society, energy rate density has increased by roughly 1 millionfold. Chasson is careful to say that no directionality or purpose is implied, but the trend is empirically undeniable. The universe has, as a matter of measurable fact, produced increasingly complex structures over time, and the rate of complexification appears to be accelerating. Now, a reasonable objection is that the second law of thermodynamics should prevent this. Entropy, the measure of disorder, must always increase in an isolated system, and the universe is, as far as we know, an isolated system. So how can complexity increase while entropy increases? The answer came from Ilya Prigogine, who won the Nobel Prize in Chemistry in 1977. Prigogine showed that systems driven far from equilibrium can undergo spontaneous self-organization. He called them dissipative structures, a hurricane, a convection cell, a living organism. These are all systems that maintain internal order by exporting more entropy to their environment than the order they create within themselves. A living cell is an island of exquisite order in an increasingly disordered sea. The cell does not violate the second law. It exploits it. It serves the entropy gradient. Prigogine put it beautifully. Increase in entropy is not an increase in disorder, for order and disorder are created simultaneously. The universe gets messier overall, but within that mess, pockets of astonishing complexity emerge, maintain themselves, and grow. Stuart Kaufman, a MacArthur Fellow at the Santa Fe Institute, pushed this further. He argued that natural selection alone cannot explain the degree of biological order we observe. Much of it, he claimed, is order for free, spontaneous self-organization that occurs when chemical systems cross a critical threshold of diversity. His concept of autocatalytic sets, collections of molecules that catalyze each other's formation, offers a mechanism for the origin of life that does not require a stroke of astronomical luck. Once a chemical soup is complex enough, a self-sustaining metabolic network pops into existence almost inevitably. Kaufman also introduced the concept of the adjacent possible, the set of all states, one step away from the current state. At every moment, the universe has a set of possible next moves. As complexity increases, the adjacent possible expands. The number of possible proteins, 200 amino acids, long is 10 to the power of 260. Compare that to the roughly 10 to the 80th particles in the observable universe. The space of biological possibility is so incomprehensibly vast that the universe is fundamentally non-ergodic above atomic scales. It can never explore all possible configurations. Every step into the adjacent possible opens new doors that did not exist before. Kaufman proposed what he called a fourth law of thermodynamics, that biospheres persistently increase the diversity of what can happen next. And his conclusion has an almost Teilhardian ring to it. If ever we are to attain a final theory in biology, he wrote, we will surely have to understand the commingling of self-organization and selection. We will have to see that we are the natural expressions of a deeper order. Ultimately, we will discover in our creation myth that we are expected after all. Expected after all. That is a scientist talking, not a priest. Simon Conway Morris, the Cambridge paleontologist, famous for his work on the Burgess Shale, takes Kaufman's argument in an even more pointed direction. Conway Morris studies convergent evolution, the phenomenon where completely unrelated lineages independently evolve the same solution to the same problem. The camera eye has evolved independently at least 40 times. Echolocation evolved independently in bats and dolphins. Flight evolved independently in insects, pterosaurs, birds, and bats. Intelligence, broadly defined, has evolved independently in primates, cetaceans, corvids, and cephalopods. Octopuses, whose lineage diverged from ours over 500 million years ago, solve puzzles, use tools, and recognize individual human faces. Conway Morris argues that this pattern of convergence means the space of biological possibility is not a vast open plain where anything can happen. It is a landscape with deep attractors, valleys that evolution repeatedly falls into regardless of starting conditions. And the deepest attractor of all, he argues, is intelligence. If you reran the tape of life on Earth as Gould famously proposed, you would not get humans, but you would very likely get something that thinks. The implications for the omega point question are significant. If intelligence is not a fluke, but a convergent attractor, then the universe is not merely compatible with the emergence of mind. It is, in some deep structural sense, biased toward it. The deck is not just fine-tuned for life, it may be fine-tuned for thought. But there is a dissenting view, and it is important. Stephen Jay Gould, the Harvard paleontologist, argued that the apparent increase in complexity over evolutionary time is a statistical artifact. Life started at a left wall of minimum complexity. A random walk from a left wall necessarily produces a longer right tail. Bacteria remain the dominant life form on Earth. The fact that some lineages have become more complex does not mean evolution has a direction. It means the variance has expanded. The debate between Gould and Kaufman, between Conway Morris and the gradualists, between those who see direction and those who see drift, remains one of the deepest unresolved questions in biology. But here is what is not in dispute. The universe has produced, over 13.8 billion years, structures of breathtaking complexity. And those structures include things that think. Which brings us to the strangest idea in this entire story. An idea that started with one of the most important physicists of the 20th century and has been gaining momentum ever since. The idea that the universe is not made of matter or energy, but of information. John Archibald Wheeler was not a fringe figure. He was one of the titans of 20th century physics. He worked with Niels Bohr on nuclear fission. He coined the term black hole. He mentored Richard Feynman and Kip Thorne. He was, by any measure, one of the most respected physicists who ever lived. And in 1989, at a conference at the Santa Fe Institute, he proposed something that sounded, on its face, insane. It from bit, he called it. The idea that every item of the physical world has at bottom, at a very deep bottom in most instances, an immaterial source and explanation. That what we call reality arises, in the last analysis, from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin, and this is a participatory universe. Wheeler was saying that the most fundamental ingredient of reality is not matter, not energy, not space-time, information, binary choices, yes or no, 1 or 0. Bit by bit, the universe is constructed from answers to questions. And the questioners, the observers, are not passive spectators of a pre-existing reality. They are participants in bringing it into being. He illustrated this with a game he called Negative 20 Questions. In the standard version, one person leaves the room, the others choose a word, and the person returns and asks yes or no questions to figure out the word. In Wheeler's version, no word is chosen in advance. Each respondent answers freely, constrained only by consistency with all previous answers. The word emerges from the questions themselves. It was not determined before the questioning began. Reality, Wheeler suggested, works the same way. The universe does not have a definite state before it is observed. Observation, measurement, the posing of questions, these are what give the universe its properties. This was not mysticism. Wheeler was drawing on the deepest implications of quantum mechanics, particularly his own delayed choice experiment, which he proposed in 1978 and which was experimentally confirmed in 1984. In this experiment, the choice of measurement apparatus determines whether photons display wave or particle behavior, even when that choice is made after the photons have already traveled their path. Wheeler concluded that we are participators in bringing into being not only the near and here, but the far away and long ago. Behind it all, he wrote, is surely an idea so simple, so beautiful, that when we grasp it in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? Wheeler's it from bit planted a seed that has grown into one of the most active areas of modern theoretical physics. Gerard 't Hooft proposed the holographic principle in 1993. Leonard Susskind gave it mathematical form. Juan Maldecena's 1997 paper on the ADS/CFT correspondence, now the most cited paper in high-energy physics with over 20,000 citations, showed that a gravitational theory in a volume of space is mathematically equivalent to a non-gravitational theory on its boundary. Reality in 3 spatial dimensions can be perfectly encoded on a 2-dimensional surface. As Susskind wrote, the 3-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant 2-dimensional surface. Jacob Bekenstein captured the implication. Scientists, he wrote, may regard the physical world as made of information, with energy and matter as incidentals, but the deepest confirmation of the information paradigm came from a paradox that tormented physics for nearly 50 years. In 1975, Stephen Hawking showed that black holes emit radiation and eventually evaporate. The problem is that this radiation appears to carry no information about what fell in. If a black hole swallows a library and then evaporates, where do the books go? Quantum mechanics insists that information cannot be destroyed. General relativity insists that nothing escapes a black hole. For decades, these 2 pillars of physics stood in direct contradiction. Hawking initially argued that the information was genuinely lost, which would have meant quantum mechanics breaks down in the presence of gravity. He bet Kip Thorne a set of encyclopedias against John Preskill's claim that information must survive. In 2004, Hawking conceded the bet and gave Preskill a baseball encyclopedia, but the mechanism by which information escapes remained mysterious until 2019, when a series of papers by Netta Engelhardt, Ahmed Almhairi, Geoffrey Pennington, and others introduced the island formula. Using techniques from quantum information theory, they showed that information does escape the black hole, encoded in subtle quantum correlations in the Hawking radiation. The proof required treating the black hole interior as an information theoretic object, rather than a purely geometric one. Information 1. Reality, at its deepest level, appears to be made of information. The digital physics movement had been saying this for decades, though mostly from the margins. Konrad Zuse, the German engineer who built the first programmable computer, proposed in 1969 that the universe is a cellular automaton. Edward Fredkin at MIT elaborated the idea in 1978. Stephen Wolfram devoted a 1,200-page book to it in 2002. Their claim is that reality is not continuous, but discrete, not analog, but digital, not described by mathematics, but constituted by computation. The universe is not like a computer. It is a computer. Seth Lloyd at MIT calculated in 2002 that the observable universe has performed approximately 10 to the 120th elementary quantum operations on approximately 10 to the 90th bits since the Big Bang. The universe, he said, is a quantum computer. What is it computing? Its own dynamical evolution. As the computation proceeds, reality unfolds, and this is where we need to pause and notice something. Because if you have been following the thread, from Teilhard's noosphere to Chardin's energy rate density, to Wheeler's et from bit to Lloyd's universe's computer, a pattern is emerging. The universe appears to be generating complexity at an accelerating rate. That complexity includes information processing, and the most complex information processing structure we know of, the human brain, has now created artificial intelligence systems that are themselves accelerating the process further. The thing that the universe spent 13.8 billion years building is now building something new, and it is building it fast. But we are getting ahead of ourselves because we still need to meet the man who tried to put actual numbers on the omega point, the man who attempted to prove, using physics, that God is a necessary consequence of the laws of nature. Frank Jennings Tipler was born on February 1st, 1947, in Andalusia, Alabama. He earned his physics degree from MIT and his doctorate from the University of Maryland in global general relativity, the same rarefied mathematical framework developed by Penrose and Hawking. He worked under John Archibald Wheeler himself at the University of Texas. His early fame came from the Tipler cylinder, a 1974 paper showing that a sufficiently massive, infinitely long rotating cylinder would warp space-time to allow time travel via closed time-like curves. His 1986 collaboration with John Barrow produced the anthropic cosmological principle, a rigorous treatment of the anthropic principle that defined what they called the final anthropic principle. Intelligent information processing must come into existence in the universe, and once it comes into existence, will never die out. Martin Gardner, the legendary mathematics columnist, promptly dubbed this the completely ridiculous anthropic principle, or crap. But Tipler was just getting started. In 1994, he published a book with one of the most audacious opening statements in the history of science, The Physics of Immortality, with the subtitle, Modern Cosmology, God, and the Resurrection of the Dead. The preface reads, and I am not making this up. This book is a description of the omega point theory, which is a testable physical theory for an omnipresent, omniscient, omnipotent God who will one day in the far future resurrect every single one of us to live forever in an abode which is in all essentials the Judeo-Christian heaven. Where Teilhard had used spiritual language Tipler used equations. Where Teilhard invoked Christ, Tipler invoked computation, the Bekenstein bound, and the final cosmological singularity. The theory is intricate, but the core argument is surprisingly elegant. Step 1. The universe must be closed, meaning its density is high enough that expansion eventually halts and reverses, collapsing back toward a big crunch, a final singularity. Step 2. Before that collapse, intelligent life must spread throughout the entire universe. Tipler envisioned mind children, uploaded human consciousness running on quantum computers dispersed via self-replicating probes at up to 90% of the speed of light. Step 3. As the universe contracts, temperatures and energy densities diverge toward infinity. The proper time remaining before the final singularity is finite, but here is the key insight. The rate of information processing increases hyperbolically as the singularity approaches. So even though the physical time remaining is finite, the number of computational operations that can be performed is actually infinite. Beings living through the collapse would experience infinite subjective time, an eternity, compressed into the final, finite moments of the universe. Step 4. The Bekenstein bound, a fundamental limit on the amount of information in a finite region of space, forces the final singularity to be a single point, not a chaotic collection of disconnected regions. This is the omega point, a state of infinite information processing capacity, a state that possesses omniscience because it processes all information, omnipotence because it controls all matter and energy, and omnipresence because it is the final state of all space-time. Tipler identified this with God, and he claimed this God would resurrect every person who has ever lived by reconstructing their quantum states from the information available in the omega point singularity. The book includes a 123-page appendix for scientists with mathematical proofs. Tipler himself conceded that fully appreciating the appendix would require the equivalent of 3 doctoral degrees. The reactions from the physics community range from grudging respect to withering scorn. George Ellis wrote in Nature that it was a masterpiece of pseudoscience, the product of a fertile and creative imagination unhampered by the normal constraints of scientific and philosophical discipline. Lawrence Krauss said he had racked his brains to come up with a more extreme example of uncritical and unsubstantiated arguments in print by an intelligent professional scientist, and could not. Sean Carroll described Tipler as having become a crackpot, but Kip Thorne, the Nobel laureate from Caltech, offered a more nuanced assessment. Let me just say that I think big pieces of Frank's argument are brilliant and beautifully done, he said, but it is in the leaky joints between the pieces where I think the problems lie. Tipler was not content to offer a theory that was merely interesting. He wanted it to be testable. In the tradition of real science, he made specific, falsifiable predictions. He predicted the Hubble constant should be no more than 45 kilometers per second per megaparsec. He predicted the Higgs boson mass would be 220 plus or minus 20 giga-electron volts. He predicted the top quark mass would be 185 plus or minus 20 giga-electron volts, and he predicted the universe's density parameter would be greater than 1, indicating a closed universe destined for collapse. Then the results came in. The top quark, discovered at Fermilab, in 1995, weighed in at approximately 180 giga-electron volts, right in Tipler's predicted range. A hit, a genuine, verified prediction of a previously unknown physical parameter derived from a theory about God. Physicists who had laughed at the theory went quiet for a moment, just for a moment. But then the other predictions crashed. The Higgs boson, discovered at CERN in 2012 after decades of searching with the Large Hadron Collider, came in at 125 giga-electron volts, nearly 100 giga-electron volts below Tipler's prediction. The Hubble constant, measured by multiple independent methods, consistently returned values around 67 to 73, well above Tipler's ceiling of 45. And then came the bombshell of 1998. Tipler's theory did not just need specific particle masses. It needed the universe to stop expanding and fall back in on itself. It needed a big crunch. It needed the expansion of the universe to be decelerating. The book's dedication reveals the emotional engine beneath the mathematics. It is dedicated to Tipler's wife's grandparents, who were killed in the Holocaust. A visit to a Nazi death camp, Tipler wrote, reinforced his conviction that there is nothing uglier than extermination. He was trying to prove that the universe would not allow death to be final, that physics itself guaranteed resurrection. And then, in 1998, the theory appeared to die. Two independent research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, announced a discovery that would earn all three the Nobel Prize. The expansion of the universe was not slowing down. It was speeding up. Something was pushing galaxies apart faster and faster. They called it dark energy, and it appeared to make up roughly 68% of the total energy content of the universe. This was devastating for the omega point theory. Tipler's framework absolutely required a big crunch. An eternally accelerating universe would never recollapse. It would just expand forever, getting colder and emptier until every star burned out, every black hole evaporated, and all that remained was a thin gruel of low-energy photons drifting through infinite darkness. Heat death, the exact opposite of convergence. David Deutsch, who had defended the omega point physics in his 1997 book, The Fabric of Reality, subsequently rejected it. Refuted, he said, ruled out by observation. In a 2024 interview, Tipler admitted to science journalist John Horgan that this was the worst mistake of his life. Not because the universe was accelerating, but because he had not predicted it. He could have, he said, and should have. The math was there. He just had not done it right. But Tipler did not give up. He proposed that the accelerating expansion was not permanent, but temporary. That the standard model of particle physics contains a natural mechanism for life to control dark energy. His argument is that the observed cosmological constant is due to the Higgs field not being in its absolute vacuum state. If intelligent life eventually develops, what Tipler calls baryon burning, reverse baryogenesis, the annihilation of baryons to convert them into leptons and energy. This would force the Higgs field toward its absolute vacuum, cancelling the positive cosmological constant and allowing the universe to recollapse. In other words, in Tipler's updated theory, the omega point does not just happen. Life makes it happen. The universe needs intelligence to reach its destiny. Most physicists dismiss this as increasingly untethered speculation. But here is where the story takes its strangest turn yet. Because in 2025, something happened that nobody expected. The Dark Energy Spectroscopic Instrument, or DESI, is the most ambitious spectroscopic survey of the universe ever attempted, mounted on the Male 4-meter telescope at Kitt Peak National Observatory in Arizona. It can measure the spectra of 5,000 objects simultaneously. Its goal is to create the most detailed, three-dimensional map of the universe ever made, covering roughly 11 billion years of cosmic history. In March of 2025, the DESI collaboration released its second dataset. Using approximately 15 million galaxy and quasar redshifts, they found strengthened evidence for evolving dark energy at 2.8 to 4.2 sigma significance. The dark energy equation of state parameter appeared greater than -1, with dark energy's influence weakening over time. Let me translate that. Standard cosmology assumes dark energy is a cosmological constant, unchanging forever. What DESI found is that dark energy might not be constant. It appears to be fading, getting weaker. And if dark energy is getting weaker, then the thing everyone assumed about the fate of the universe, that it will expand forever, may be wrong. In September of 2025, Cornell physicist Henry Tai published a model based on the new data predicting that the universe will expand to a peak in roughly 11 billion years and then contract, ending in a big crunch approximately 20 billion years from now. To make the first 119 decimal places of the vacuum energy zero is most certainly no accident, Susskind had said years earlier, and now the 120th decimal place appeared to be changing. In November, Professor Youngwook Lee of Yonsei University published a study in the monthly notices of the Royal Astronomical Society, arguing that when you correct for age bias in type Psi I supernovae, standard candles used to measure cosmic expansion, the universe's expansion already appears to be decelerating. If confirmed, this would overturn the discovery that won the 2011 Nobel Prize. Now let me be very clear. These results are controversial. Nobel laureate Adam Rees called Lee's study flawed. The scientific community is divided. 5 sigma, the threshold for a confirmed discovery in physics, has not yet been reached for the DESI evolving dark energy result. We are at 4.2 sigma on some analyses, which is close, tantalizingly close, but close is not confirmed. However, what is no longer true as of 2025 is that the possibility of a big crunch is dead. For 27 years, since 1998, the door had been firmly shut. That door is now cracked open, and behind it, whether you find it exhilarating or terrifying, is the shadow of the omega point. And the DESI data was not even the strangest thing to come out of 2025 cosmology. The James Webb Space Telescope had been in operation since mid-2022, and almost immediately it started breaking things. Models, predictions, assumptions that had been comfortable for decades. JWST found galaxies that were far too massive, far too bright, and far too structurally mature for their age. Within the first billion years after the Big Bang, Webb identified galaxies with stellar masses that should have taken billions of years to accumulate. It found a 5-galaxy merger at just 800 million years post-Big Bang, a gravitational dance of staggering complexity happening when the universe was barely a toddler. The early universe was not the simple, sparse, slowly evolving place the Standard Model predicted. It was rich. It was complex. It was building things faster than anyone thought possible. This matters for the omega point question because it reinforces Chardin's observation about accelerating complexity. The universe did not wait around. It started building complex structures almost immediately, as if it were in a hurry. Meanwhile, a different kind of evidence emerged from chemistry. In 2023, Lee Cronin at the University of Glasgow and Sarah Imari Walker at Arizona State University published a paper in Nature introducing something they called assembly theory. The idea is elegantly simple. Take any molecule and ask how many joining operations are required to build it from basic building blocks. That number is the molecule's assembly index. Cronin and Walker showed that molecules with an assembly index above 15 are found exclusively in samples associated with living systems. No known abiotic process produces molecules that complex. The implication is profound. Assembly theory provides a measurable, empirical boundary between chemistry and life. It suggests that life is not a vague emergent property, but a detectable physical phenomenon, something the universe does when molecular complexity crosses a specific threshold. And it connects back to Kaufman's work on autocatalytic sets. The universe appears to have a built-in tendency to cross that threshold, given enough time and the right conditions. There is also the question that Nick Bostrom, the Oxford philosopher, posed in 2003, and that has become more unsettling with every advance in computing power. His simulation argument is a trilemma. One of three things must be true. Either virtually all civilizations at our level of development go extinct before they develop the ability to run realistic simulations of consciousness, or virtually all civilizations that survive choose not to run such simulations, or we are almost certainly living inside a simulation right now. The math is surprisingly difficult to escape. If any civilization anywhere ever develops the ability to simulate conscious beings in large numbers, then the number of simulated minds vastly exceeds the number of biological minds. And any given conscious experience is statistically more likely to be simulated than real. If we are in a simulation, then the universe was designed not by a bearded figure in the clouds, but by beings who made themselves be in a simulation, running inside a simulation, stacked like Russian dolls all the way up to something that Tipler and Teilhard might recognize. Max Tegmark at MIT pushed the boundary even further. He proposed that the universe does not just use mathematics to describe reality. Mathematics is reality. His mathematical universe hypothesis states that all structures that exist mathematically also exist physically. Every consistent set of equations is a universe somewhere. We are self-aware substructures within a mathematical object, conscious equations that have figured out they are equations. And Lee Smolin at the Perimeter Institute in Canada offered perhaps the most creative alternative to both design and the multiverse lottery: cosmological natural selection. Smolin proposed that every black hole that forms spawns a new universe on the other side of its singularity, with physical constants slightly different from the parent universe. Universes that produce lots of black holes produce lots of offspring. Over many generations, universes that are finely tuned for black hole production dominate the cosmic population. And it just so happens that the conditions that produce lots of black holes, massive stars, rich chemistry, long-lived stellar nurseries are almost exactly the conditions that produce life. Darwinian evolution operating not on organisms, but on entire universes. Smolin's theory is testable. He predicted that no neutron star should exceed approximately 2 solar masses, because heavier neutron stars would collapse to black holes more efficiently, which would be selected for. So far, observations are broadly consistent with this, though debate continues. But the elegance of the idea is remarkable. It explains fine-tuning without invoking either a designer or an infinite number of unobservable parallel worlds. It replaces teleology with evolution. The universe is finely tuned not because someone intended it, but because cosmic natural selection favored it. Every one of these ideas, the simulation, the mathematical universe, the cosmological Darwinism, is an attempt to answer the same question. Why does the universe look like it was designed for something? And every answer, including the answer that it was not designed at all, raises more questions than it resolves. But let us step back from cosmology for a moment, because there is another piece of this puzzle that we have not yet addressed. And it may be the most important piece of all. We have talked about fine-tuning. We have talked about complexity. We have talked about information. We have not yet talked about the thing that makes all of these questions matter in the first place. The thing that turns a universe of particles and forces into a universe that contains experience, wonder, awe, and the ability to ask why. We have not talked about consciousness. David Chalmers, an Australian philosopher now at NYU, gave the problem its definitive name in 1995. He called it the hard problem of consciousness. The hard problem is this: even after you have explained every functional and behavioral aspect of the brain, every neuron, every synapse, every chemical signal, the question remains: why is the performance of these functions accompanied by experience? Why is there something it is like to see red, to feel pain, to taste chocolate? Why is not all of this information processing going on in the dark? Chalmers proposed a thought experiment that cuts right to the heart of it. Imagine a zombie, not the Hollywood kind, a philosophical zombie, a being that is atom for atom identical to a conscious human being. It behaves identically. It responds to stimuli identically. If you asked it how it feels, it would give the same answer a conscious person would. But there is no inner experience. All is dark inside. No one is home. If such a zombie is even conceivable, Chalmers argued, then consciousness cannot be fully explained by physical facts alone. Something is missing from our picture of reality. Chalmers has increasingly suggested that consciousness may be a fundamental feature of the universe, not something that emerges from complex arrangements of matter, but something that exists at the bedrock level of reality, like electromagnetism or gravity. The only things that are irreducible to lower-level facts, he wrote, are fundamental laws of nature. Since consciousness is irreducible, it too is fundamental. Meanwhile, Giulio Tononi, a neuroscientist at the University of Wisconsin-Madison, developed the most mathematically rigorous theory of consciousness anyone has ever proposed. He called it Integrated Information Theory, or IIT. The core idea is deceptively simple. Consciousness is integrated information, which Tononi denotes with the Greek letter phi, any system that integrates information, that is more than the sum of its parts in terms of information processing, possesses some degree of consciousness. A photodiode that detects light has a tiny amount of Phi. A thermostat has a bit more. A human brain, with its roughly 86 billion neurons and 100 trillion synaptic connections, working as an irreducibly integrated whole, has an enormous amount. The implications are startling. If consciousness is identical with integrated information, then consciousness is not something special that brains do. It is something that any sufficiently integrated system does. A sufficiently complex network of logic gates could be conscious. A sufficiently interconnected ecology could be conscious. And taken to its logical conclusion, the universe itself, if its components are sufficiently integrated, could be the most conscious entity in existence. Not everyone was buying it. In 2014, theoretical computer scientist Scott Aaronson published a critique that landed like a grenade. He showed that under IIT's mathematical formalism, a simple grid of inactive XOR logic gates would generate a Phi value unboundedly larger than the human brain. A grid of switches doing nothing would, according to the theory, be far more conscious than Einstein. Aaronson expected Tononi to retreat. Instead, Tononi embraced the conclusion. He said the theory predicts what it predicts, and if that means certain arrangements of matter are more conscious than humans, then so be it. Aaronson was stunned. He called it the gutsiest move he had ever seen in his career. But theories need testing, not just admiration. And in 2025, the most ambitious test of consciousness science ever attempted delivered its results. The Cogitate study, a massive adversarial collaboration published in Nature, pitted IIT against its main rival, global neuronal workspace theory, in a series of pre-registered experiments designed to distinguish between them. Christoph Koch, who had led the consciousness research program at the Allen Institute, had made a famous bet with David Chalmers 25 years earlier that science would identify the neural correlates of consciousness by 2023. When Cogitate's results came in, neither IIT nor Global Workspace was definitively vindicated. Koch conceded the bet. At a conference in front of hundreds of colleagues, he handed Chalmers a case of fine wine. The hard problem of consciousness remained exactly as hard as it had been in 1995. But here is what Cogitate did reveal, and this is crucial. Both theories had correct predictions and incorrect predictions. The data did not fit neatly into either framework. Consciousness appears to be doing something that neither our best bottom-up theory nor our best top-down theory can fully capture. Whatever consciousness is, it seems to resist every attempt to reduce it to a simple mechanism. It keeps slipping through the net. This is not a fringe position anymore. Philip Goff, a philosopher at Durham University, has spearheaded a 21st century renaissance of Panpsychism, the idea that consciousness is a basic feature of matter. His argument, laid out in Galileo's Error in 2019 and Why in 2023, goes like this. When Galileo founded modern physics, he made a deliberate decision to describe the world in purely quantitative mathematical terms. Length, mass, velocity, charge. He stripped away all qualitative properties, the colors, the sounds, the textures, the experiences, and treated them as mere appearances in the minds of observers rather than features of reality itself. This was spectacularly successful for physics. but it created a gap. Physics tells us what matter does. It does not tell us what matter is. The only place where the intrinsic nature of matter is directly known, as opposed to inferred from behavior, is in our own conscious experience. Panpsychism proposes that consciousness is that intrinsic nature everywhere. Goff's more radical position, Cosmopsychism, proposes that the universe as a whole is conscious, and individual consciousness is derived from cosmic consciousness rather than the other way around. In Y, he goes further still, arguing that the universe's wave function is a conscious entity that is aware of the complete future consequences available to it and acts by choosing the best one. This would provide a panpsychist explanation for fine-tuning. The universe chose these constants because they lead to the richest possible conscious experience. Roger Penrose approached the problem from a completely different angle. In The Emperor's New Mind in 1989 and Shadows of the Mind. In 1994, Penrose argued that consciousness is non-computational. Using Gödel's incompleteness theorem, he showed that mathematical understanding transcends any algorithmic process. There are truths that humans can see are true, but that no computer, no matter how powerful, running any algorithm, no matter how clever, can prove. This means, Penrose argued, that whatever consciousness is, it is not a computation. It is something physics does not yet understand. With anesthesiologist Stuart Hameroff, he developed a theory called orchestrated objective reduction, which proposes that quantum superpositions in microtubules, tiny protein structures inside neurons, undergo gravitational self-collapse, and these collapse events constitute moments of conscious awareness connected to fundamental space-time geometry. Consciousness, in this view, is not an accident of biology. It is a feature of the geometry of space-time itself. For decades, most neuroscientists dismissed OR as fantasy. Quantum effects in the brain, they said, would be destroyed instantly by thermal noise. The brain is too warm, too wet, too chaotic for quantum coherence to survive. The theory was considered beautiful but biologically impossible. But then the evidence started changing. In 2014, researchers demonstrated quantum coherence in photosynthesis at room temperature. In 2023, studies on bird navigation confirmed quantum entanglement in biological molecules involved in magnetoreception. And in 2024, a team published evidence of superradiance in tryptophan networks within microtubules, the exact structures Hameroff had identified decades earlier. Superradiance is a quantum optical effect that requires coherent behavior among many molecules acting in concert. Finding it in microtubules at biological temperatures was supposed to be impossible, but there it was. This does not prove OR is correct, but it eliminates the primary objection against it. For 30 years, critics said quantum coherence in warm, wet biology was physically impossible. The evidence now says otherwise. Quantum effects in biological tissue at body temperature are no longer theoretical. They are measured, and the fact that these effects were found in the precise cellular structures that Hameroff identified in the 1990s, before the technology to test them even existed, is either a remarkable coincidence or a sign that the theory is tracking something real. Whatever consciousness turns out to be, the quantum option is back on the table. Penrose stated it as clearly as anyone ever has. My claim is that there has to be something in physics that we do not yet understand, which is very important, and which is of a non-computational character. It is not specific to our brains. It is out there, in the physical world. Somewhere else entirely, he also said something that, coming from a Nobel Prize-winning physicist, lands like a thunderbolt. Somehow, our consciousness is the reason the universe is here. Now, I need to tell you about the people who think all of this is wrong, because they have powerful arguments, and ignoring them would be intellectually dishonest. Steven Weinberg, Nobel laureate, one of the architects of the Standard Model of particle physics, wrote what may be the most quoted sentence in the history of science and meaning debates. It appears in the first 3 minutes, published in 1977, and he wrote it, fittingly, on an airplane at 30,000 feet. It is almost irresistible for humans to believe that we have some special relation to the universe, that human life is not just a more or less farcical outcome of a chain of accidents reaching back to the first 3 minutes. The more the universe seems comprehensible, the more it also seems pointless. But he did not stop there. And the part people forget changes the meaning entirely. But if there is no solace in the fruits of our research, there is at least some consolation in the research itself. The effort to understand the universe is one of the very few things which lifts human life a little above the level of farce and gives it some of the grace of tragedy. Weinberg was not saying that life is meaningless. He was saying that the universe does not provide meaning. We create it. The act of trying to understand is itself the meaning. Jacques Monod, Nobel laureate in physiology, wrote the definitive statement of cosmic existentialism in chance and necessity in 1970. The ancient covenant is in pieces. Man knows at last that he is alone in the universe's unfeeling immensity, out of which he emerged only by chance. His destiny is nowhere spelled out, nor is his duty. The kingdom above or the darkness below, it is for him to choose. And later, the universe was not pregnant with life, nor the biosphere with man. Our number came up in the Monte Carlo game. Richard Dawkins, in River Out of Eden in 1995, put it even more bluntly. The universe that we observe has precisely the properties we should expect if there is, at bottom, no design, no purpose, no evil, no good, nothing but blind, pitiless indifference. Sean Carroll, in The Big Picture in 2016, laid out what he calls poetic naturalism. There is no separate realm of the supernatural, spiritual, or divine, nor is there any cosmic teleology or transcendent purpose inherent in the nature of the universe. The laws of physics are not formulated in teleological terms. What matters is the current state, not a future goal. The universe does not care what we do. Our task is to make peace with that fact and take pride in the fact that we care anyway. And Daniel Dennett, in Darwin's Dangerous Idea, drew a distinction between what he called skyhooks and cranes. Skyhooks are mind-first explanations. A cosmic intelligence designed the universe. A superintellect monkeyed with physics. The universe is evolving toward God. Cranes are bottom-up mechanisms grounded in physics, natural selection, self-organization, dissipative structures. Dennett's argument is that there are no skyhooks anywhere in nature. Every instance of apparent design can be explained by cranes. Evolution is an algorithmic process, mindless, mechanical, substrate neutral, and yet sufficient to generate every ounce of complexity we observe. These are not weak arguments. They represent the considered views of some of the smartest people who have ever lived, and the heat-death problem remains the strongest physical objection to any omega point scenario. The current scientific consensus points toward eternal accelerating expansion, leading to maximum entropy. Stars will continue forming for perhaps 10 to the 12th to 10 to the 14th years. Then fuel runs out. Black holes evaporate over 10 to the 67th to 10 to the 100th years via Hawking radiation. After that, nothing but low-energy photons and leptons drifting through an ever-expanding void. No energy gradients, no information processing, no thought, no experience, just silence forever. Lawrence Krauss and Glenn Starkman further argued in 1999 that even Freeman Dyson's proposal for eternal intelligence in an open universe fails. Any finite material system has a finite number of accessible quantum states. As the temperature of the universe drops below the energy gap between ground and excited states, the system becomes permanently frozen. While the universe might expand forever, they wrote, the integrated conscious lifetime of any civilization will be finite. That is the prosecution's case, and it is strong. But then there is the 2025 plot twist we already discussed. The DESI data suggesting dark energy is weakening. The TIE model predicting a big crunch in 20 billion years. The Lee study suggesting the universe may already be decelerating. None of these are confirmed, but all of them point in the same direction, away from heat death, toward collapse, toward convergence. And while the cosmologists argue about the fate of the universe, something else is happening right now, right here on Earth, that Teilhard de Chardin predicted 100 years ago, and that adds an entirely new dimension to the omega point question. Artificial intelligence is accelerating the noosphere. Ray Kurzweil, the inventor and futurist, has for decades described cosmic history as 6 epochs of accelerating information processing: physics and chemistry, biology, brains, technology, the singularity, which he places around 2045, and finally, the universe wakes up. His law of accelerating returns describes exponential technological progress that is itself accelerating, and his prediction for artificial general intelligence, human-level AI, by 2029, which seemed wildly optimistic when he made it in 2005, is now mainstream among industry leaders. Kurzweil wrote, and this is the line that connects everything: we will eventually permeate the universe with intelligence, causing the universe itself to awaken. That is about as close to God as I can imagine. For decades, serious scientists treated Kurzweil as a brilliant eccentric. Interesting ideas, they said, but the timelines are fantasy. A GI by 2029? Absurd. The brain is too complex. Intelligence is too poorly understood. We are centuries away, if it is possible at all. And then, 2023 happened. Large language models crossed a threshold that nobody outside a handful of AI labs had predicted. Systems that could reason, write code, pass medical board exams, score in the 99th percentile on bar exams, and engage in scientific reasoning emerged seemingly overnight. The reaction from the AI community was not celebration. It was shock. The timelines that everyone had dismissed as science fiction were suddenly mainstream. By 2025, Jensen Huang, the CEO of NVIDIA, said publicly that AGI was 5 years away. Eric Schmidt, former CEO of Google, placed it within 3 to 5 years. Masayoshi Son, CEO of SoftBank, predicted artificial superintelligence, systems smarter than all of humanity combined, within 10 years. Dario Amodei, CEO of Anthropic, wrote that the most profound changes in human history could come within the next 2 to 3 years. These are not fringe voices. These are the people building the systems, and they are terrified and exhilarated in roughly equal measure. David Deutsch, the physicist who pioneered quantum computing, offers the philosophical framework that connects AI to the omega point. In The Beginning of Infinity, published in 2011, Deutsch argues that knowledge, specifically explanatory knowledge, has universal reach. A mind capable of creating explanations can, in principle, understand anything that is understandable and solve any problem that is solvable. There is no limit to what such a mind can accomplish, given sufficient time and resources. Deutsch calls humans the most significant entities in the cosmic scheme of things, because we are the only known things capable of creating explanatory knowledge. But he is careful to note that this significance is not about biology. It is about what we can do, and anything that can create explanatory knowledge, including an artificial intelligence, inherits that cosmic significance. If Deutsch is right, and if AGI or superintelligence emerges in the next decade, then the noosphere is about to undergo a phase transition. Not a gradual thickening, but a sudden leap, like water turning to ice, like single-celled life becoming multicellular. Teilhard predicted acceleration. He did not predict the speed. Think about what is happening right now through the lens of Teilhard's framework. The noosphere, the sphere of thought enveloping the planet, is thickening at a pace that would have staggered even Teilhard. Every smartphone is a node. Every satellite link is a synapse. Every large language model is a new kind of cognitive process operating at superhuman scale. The global brain is not a metaphor anymore. It is infrastructure. It is fiber optic cables and data centers and neural networks processing more information in a day than all of humanity processed in a year just a few decades ago. And it is not just AI. The James Webb Space Telescope has been revealing an early universe far more complex than anyone expected. Galaxies that should not exist yet, massive, structured, full of heavy elements, appearing within the first billion years after the Big Bang. A 5-galaxy merger at roughly 800 million years post-Big Bang. The universe was assembling complexity faster than our models predicted. The standard formation timeline, which assumed galaxies needed billions of years to reach maturity, has been shattered. Meanwhile, in 2023, chemist Lee Cronin and physicist Sarah Imari Walker published Assembly Theory in Nature, proposing a new way to measure complexity and detect the influence of selection, evolution, and life on molecular structure. Their assembly index quantifies the minimum number of joining operations needed to build a molecule from its fundamental parts. They found that molecules with an assembly index greater than 15 appear exclusively in living systems. No purely random chemical process produces them. Assembly theory offers, for the first time, a physics-based way to distinguish molecules shaped by evolution from molecules shaped by chance. If the universe is evolving toward complexity, assembly theory gives us a ruler to measure it. Teilhard wrote that there is something afoot in the universe, something that looks like gestation and birth, and from a certain angle, looking at the trajectory from single-celled organisms to global neural networks to AI systems that can reason, create, and discover, it is very hard to argue that he was wrong about the trajectory. Whether he was right about the destination is a different question. Freeman Dyson, who lived from 1923 to 2020, was one of the few elite physicists willing to take the omega point question seriously without either endorsing or dismissing it. In 1979, in a paper called Time Without End, Dyson asked a question that should have been obvious, but that almost no physicist had bothered to address. Can life survive forever in an open, eternally expanding universe? His answer was surprisingly optimistic. Dyson showed that by hibernating for increasingly long periods and waking only occasionally to think and communicate, an intelligent civilization could process an infinite number of thoughts using only a finite amount of energy. The key was that as the universe cooled, the cost of computation dropped. What you lost in speed, you gained in efficiency. Dyson calculated that a being or civilization could, in principle, sustain subjective consciousness for infinite time, experiencing infinite thoughts, even as the physical universe wound down around it. There was something deeply poignant about this vision. Intelligence, surviving at the edge of oblivion, stretching each thought across longer and longer intervals, a mind that thinks once per billion years, but thinks forever. It was the opposite of Tipler's omega point, where infinite computation happens in a finite blaze of glory at the end. Dyson's version was infinite computation, spread across an infinite whisper, but the destination was the same. Mind enduring, mind transforming itself in response to a changing cosmos, mind eventually becoming something unrecognizable to us, but continuous with us. He wrote something in that same period that still sends a chill down the spine. I do not feel like an alien in this universe. The more I examine the universe and study the details of its architecture, the more evidence I find that the universe, in some sense, must have known that we were coming. And later, even more provocatively, I do not make any clear distinction between mind and God. God is what mind becomes when it has passed beyond the scale of our comprehension. There is a view that sits between the believers and the skeptics, and it may be the most honest position of all. It is the view that the question is genuinely open, that the evidence does not conclusively support either cosmic purpose or cosmic indifference, that the fine-tuning is real and unexplained, that complexity genuinely increases and we do not fully understand why, that consciousness remains a mystery, that the fate of the universe is no longer as certain as we thought, and that the responsible thing to do is not to pick a side, but to follow the evidence wherever it leads. Arthur C. Clarke, who was no friend of organized religion, wrote something that captures this perfectly. It may be that our role on this planet is not to worship God, but to create Him. And Wheeler, always Wheeler, offered the image that haunts me most. He drew a picture of a capital U, the universe, with an eye at one end looking back at its own origin. The universe creates consciousness, and consciousness gives meaning to the universe. A self-excited circuit, a feedback loop that spans all of cosmic time. So where does this leave us? We have a universe fine-tuned to one part in 10 to the 120th power for the emergence of complexity. We have an unbroken 13.8 billion-year trajectory from hydrogen to consciousness, with energy rate density increasing 1 millionfold. we have information emerging as a serious candidate for the most fundamental ingredient of reality. We have consciousness refusing to be explained by current physics. We have a mathematical framework, flawed but not refuted, predicting that infinite computation and therefore infinite experience could occur in the final moments of a collapsing universe. We have dark energy data from 2025 suggesting that the expansion of the universe may not be permanent after all. And we have the most advanced technology our species has ever created, artificial intelligence, accelerating the growth of the noosphere in real time. Against this, we have the mainstream scientific consensus that the universe is purposeless, that evolution is blind, that complexity is a local statistical fluctuation, and that the most likely fate of everything is eternal cold darkness. Both sides claim the evidence. Neither can prove the other wrong. There is a thought experiment that captures the vertigo of this situation better than any argument. Imagine the creator, as Roger Penrose described it, faced with the task of setting the initial conditions of the universe. Before this, creator lies a phase space of unimaginable vastness, representing every possible way the universe could have started. To produce a universe like ours, the creator must place a pin in a region so small that the probability of hitting it by chance is 1 in 10 to the power of 10 to the power of 123. A number so large you could not write it down, even if you used every particle in the universe as a digit. Now, you can respond to that in one of 3 ways. You can say that there is a creator who placed the pin deliberately. You can say that there are enough universes, 10 to the 500th or more, that one of them was bound to get lucky. Or you can say that we simply do not yet understand the physics well enough to know why the pin is where it is, and that future discoveries will provide a natural explanation. Each of those responses requires faith. Faith in God, faith in the multiverse, or faith in future science. None of them is empirically verifiable at present. And that is the honest truth that most popularizers of science on both sides are reluctant to admit. Teilhard de Chardin died believing that the universe was evolving toward Christ. Frank Tipler believes he can prove the omega point from the standard model of particle physics. Fred Hoyle died believing a superintellect had monkeyed with the laws of nature. Roger Penrose believes consciousness is a feature of space-time geometry. Stuart Kaufman believes we are expected after all. Philip Goff believes the universe is conscious. Ray Kurzweil believes intelligence will permeate the cosmos and cause it to wake up. Steven Weinberg believed the universe is comprehensible but pointless. Jacques Monod believed we are alone in an unfeeling immensity. Richard Dawkins believes in blind, pitiless indifference. Sean Carroll believes there is no cosmic teleology. Daniel Dennett believed there are no skyhooks, only cranes. All of them are brilliant. All of them are working from the same evidence, and they reach opposite conclusions. Here is what I think. For whatever a voice in a documentary is worth, I think the most remarkable thing about this entire story is not any single piece of evidence. It is the fact that the evidence exists at all. There is no reason, no physical law, no mathematical necessity that the universe should contain beings capable of asking whether the universe has a purpose. A universe of hydrogen and helium expanding forever into darkness would be perfectly consistent with the laws of physics. A universe without consciousness would still have stars and galaxies. It just would not have anyone around to notice them. But that is not the universe we got. We got a universe that makes carbon inside stars, that assembles carbon into self-replicating molecules, that evolves those molecules into brains, and that points those brains at the sky and whispers, "Figure me out." Whether that whisper is meaningful or accidental is the question that divides every thinker we have discussed today. I think the question of whether the universe is evolving towards something, whether complexity and consciousness are accidental byproducts or the point of the whole exercise, is the deepest question our species has ever asked. Deeper than where did we come from, because we have a pretty good answer to that. Deeper than are we alone, because that question is about our neighborhood, not our nature. The Omega Point question is about the fundamental character of reality itself. Is the universe a story with an ending or a noise that signifies nothing? And I think the honest answer, the genuinely honest answer, is that we do not know, but we are closer to knowing than we have ever been. The DESI data will reach 5 sigma or it will not. The James Webb Space Telescope will continue revealing an early universe more complex than any model predicted. Artificial intelligence will either plateau or it will continue accelerating towards something none of us can predict. Consciousness will either yield to neuroscience or it will remain the crack in the edifice of materialism that it has been for 4 centuries. What strikes me is how uncomfortable both sides are with their own conclusions. The believers in cosmic purpose have to explain why the universe allows so much suffering, so much waste, so many dead-end evolutionary experiments, so many galaxies that will never produce a single living cell. If the universe is fine-tuned for consciousness, it is doing an extraordinarily inefficient job. 99.9999% of it is empty space, lethal radiation, and temperatures that would kill anything alive instantly. Some design, but the materialists have their own discomfort. If the universe is truly purposeless, then the fact that it produced beings who crave purpose is a cruel joke, or a staggering coincidence, or an emergent property that somehow feels more real than the substrate it emerged from. Sean Carroll says the universe does not care, but he cares enough to write books about it. Dawkins says there is nothing but blind, pitiless indifference, but his outrage at indifference is itself a passionate departure from indifference. The materialist position, taken to its logical conclusion, undermines the motivation to investigate it. If nothing matters, why are you doing science? The answer, of course, is that scientists find meaning in the search itself, which sounds suspiciously like what Weinberg said, and which sounds, if you squint, like a Teilhardian claim about consciousness reaching upward. Teilhard wrote, "Remain true to yourself, but move ever upward toward greater consciousness and greater love. At the summit, you will find yourselves united with all those who, from every direction, have made the same ascent. For everything that rises must converge." Maybe he was a prophet. Maybe he was a poet with delusions of cosmological grandeur. Maybe the universe is building a god, and we are the neurons. Or maybe the universe is not building anything, and the god we keep detecting in the data is our own reflection, the pattern-seeking primate seeing faces in the clouds. But here is the thing that keeps me up at night. Even the skeptics, even the hardest-nosed materialists, cannot seem to shake the feeling that something strange is going on. Weinberg could not resist the word comprehensible. Dawkins used the word design, even if only to deny it. Carroll chose to write a book called The Big Picture, as if the universe has a picture to see. And Wheeler, perhaps the greatest physicist of the second half of the 20th century, the man who named black holes and co-authored the most important nuclear fission paper of the 20th century, spent the last decades of his life drawing a picture of the universe, looking at itself and saying, the universe gives birth to consciousness, and consciousness gives meaning to the universe. I do not know if the omega point is real. Nobody does. But I know that the question of whether the universe is going somewhere, whether 13.8 billion years of increasing complexity is a cosmic accident or a cosmic process, is not a question that science has answered. It is a question that science is still investigating. The data from DESI, the discoveries from Webb, the exponential curve of artificial intelligence, the unsolved mystery of consciousness, all of it is still in play. And if you have made it to the end of this, if you have traveled from Teilhard's trenches to Tipler's equations to the 2025 dark energy data, then you are part of the universe doing exactly what Teilhard said it was designed to do. You are matter that has become conscious of itself, reaching for understanding, grasping at something just beyond the edge of comprehension. Whether that reaching is the whole point, or just the last flicker before the lights go out, is the question that will define the next century of science. The universe is still computing, and the answer is not in yet.